So what is a capacitor, and what does it do? A capacitor is a device that ends up building up charge that you can save for some time later. It's actually very similar to a battery, except for the part that a battery runs through a chemical reaction and a capacitor works by building up charge on two parallel plates. It looks similar to what we just finished up with electric potential and parallel plates video. Now these two plates should look pretty similar. We just talked about them in the last video where we ended up looking at cathode ray tubes where electrons were fired through here to make spots on screens, which start off televisions. But what happens with a capacitor is it's not actually an empty space where we could have something like an electron flow through. What it is it's actually filled with an insulator, something that we call a dielectric. Now this dielectric is anything that keeps electrons from flowing. And the way we show that is through a box in the middle. And the easiest way that we can build up a charge on here is if we were to connect both of these end wires up to a battery. So I'm going to show that as well. Now what I've done is I've built a very simple circuit where I have one resistor, I have one battery, I have a capacitor, and I have a switch. So as I close this switch and I allow current to flow, and I'll tell you why I use the quotations in just a second, but I allow the current to flow through, what happens is the electrons end up getting a buildup. We have a negative charge on the left and it comes through and the electrons end up giving us a buildup on this side. So what is that going to do with the other plate? Well, would it do anything? Because we have an insulator in the middle. We wouldn't allow any flow of electrons to go through, so shouldn't this just remain the way it is and we just have a buildup of negative charge on the right and that be it? Actually, no. What happens is as these electrons start to build up on this side, we get more and more electrons build up, and what happens when this occurs is it pushes away the electrons from the other plate, right? So all of these electrons start to run away. What does that mean about the charge on this other plate? It should leave it positive as well as being equal in magnitude to the negative plate. No matter what, our capacitor has got to have the same charge on both plates. Now the benefit of my scenario is if I disconnect my circuit, what's going to happen to these electrons? Well, they're not going to be able to separate, and this is how we can store our charge. We have now built up a potential difference. We have built up a charge difference between one plate and the other, and now we can use it and save it for later. Now here might be a better way to show what a capacitor is. And in my diagram, I now have a pump, which acts just like my battery. I've got something that uses energy, which we're just going to draw a fan, right? What's flowing through right now is a water. So this is a water flow analogy. And at the top, I've got my capacitor. Now what I'm going to say is I'm going to say that the current of the water is going to be flowing from the bottom to the left. And as it enters into the capacitor, it's pushing through. It's trying to get back to the other side of the pump. But what this dielectric is it acts kind of like a membrane or a balloon that won't allow anything to go through. Now it doesn't act like a wall and not allow anything. What it does is it gives in a little bit to the water. And this is why I said that the current flows in parentheses. Because in actuality, none of the water goes into a circuit. It never completes. So the flow of electricity or the flow of water right now doesn't happen. But what does happen is something a little bit like this. And this dielectric gets pushed in. Right? This buildup of charge is pushing that happens, ends up pushing a little bit of excess water through. And this is what we call an induced current. Not really a true current, but it does do a little bit of a push. and that water ends up kind of flowing through the rest of the way. Well, what does this mean about if I turned off the pump? If I flick the switch, what happens? Is there anything still pushing through, still trying to make all the water go through? Well, you'd most certainly say no. But what happens with this membrane then? If there's nothing still pushing it, what happens? Well, so as the pump gets turned off, this pump ends up getting turned off, still a part of the circuit, then wouldn't this membrane, kind of like a balloon, just like if you blow it up and you let go of it, it ends up releasing all of its buildup of air, or in this case, water, right? So now the water doesn't flow forwards, but would it now end up getting pushed backwards through? And then as a result, our capacitor ends up going back to a neutral position or vertical, right? That's perfect. And this is why the current that I said was induced, is because now, as the pump is turned off and the water flows backwards, if we think about any actual electron or any water particle, it really hasn't actually changed location. If I had one that started here, and when the pump was turned on, it went in, well then once the membrane pushed back, it went right back to its initial position. So there's really actually no flow of electricity or no flow of water in this situation. The entire current was induced, or kind of like a fake current. So now we've talked about kind of the conceptual background behind it. Let's get into our formulas. A capacitor has a certain amount of capacitance, and our variable that we're going to use in our formulas is going to be C, capital C. So we measure capacitance in farads, and rarely ever would we use an actual farad in any sort of formula, because 1 farad is a lot of charge. What we would measure it in is in terms of microfarads. Now the reason I can tell you this is from our first formula that we get. And we can measure capacitance based off of charge, and we can also look at it based off of voltage. Where we have the charge buildup on our plates, so our parallel plates that we have a certain charge. We have a positive charge, and we also have a negative charge, right? And we also have the voltage, or how much push of the pump that there was to try and get our dielectric, or our membrane, to bend in. So our capacitance is measured by charge divided by voltage, right? So 1 farad is the same as 1 coulomb per volt. And if we think about coulombs, remember 1 electron is 1.6 times 10 to the negative 19th coulombs. So in order for me to get a single coulomb of charge, I would need a huge buildup of electrons with a very little bit of energy, one volt of energy. Or I can build up more push and have less electrons. But still, 1 times 10 to the negative 19th coulombs per electron. If I need 1 coulomb of charge, that is an awful lot of number of electrons. Now if I were to ask you, what dictates how much capacitance there is? What are the variables that would increase my capacitance? Let's say that I just have a setup where I have 2 plates right here, and they have a certain capacitance, right? My capacitor has a certain value, but I wanted to increase it. I wanted to give myself more capacitance, be able to hold more charge. What could I do? Well, charge is based off of distance. The farther away they are, if I were to separate my 2 plates to a farther distance, then wouldn't that mean that there wouldn't be as much interference and I could put more electrons on one side than I did in my initial condition? As well as, what if I made my bars even longer? What if I made them really big, or my plates really big? Because with more space, I can fit more electrons on a surface. Kind of like if I have more space, a bigger room, I can fit more people into it. That's actually an interesting way of thinking about it. That our plates, the bigger our plates are, the more electrons we can put on there. Just like my classroom can hold probably 50 people somewhat comfortably, but if we were to go into the gymnasium or if we went into the pack, we could easily fit 4 times the number of people. And that's just based off the total number of space. So yeah, if we opened up, we made more space, we would be able to add more electrons on there. I agree. Now the distance that you wanted to say, you said, let's increase the distance between our plates. Well, each electron really doesn't like itself. It doesn't like anybody else around it. Right? They want to stay as far away apart as possible, unless there's something to keep it there, right? So if we think that as this builds up a negative charge, there should be a positive charge that's building up over here. Well, if we separate the distance, that's kind of pulling it away from the negative or from the positive charge. And as we look into any formula that we had before, something like our E field equation, was distance was 1 over r squared. So as r increased, my value of E field decreased. That same thing happens here, is the value of charge that I could build up is going to be lower the farther distance we are apart. So if I were to look qualitatively at this, and I said that the capacitance is directly related to the area. As area increases, as I go from my small classroom to a gymnasium, my capacitance increases. I guess you could think of it as capacity, right? The maximum capacity would increase with more area, as well as capacitance is directly related to 1 over the distance. So let's put these into a formula together. Would it look something like this? Capacitance is equal to area over distance? Yeah, that's true. But there's one thing that I want to add to this. First off is, what about my dielectric? We haven't taken that into effect at all. Now, if my dielectric is something like a vacuum, where there's nothing in between it, how much resistance is there, or how easy is it going to be for an electron to hop from one plate to the other? It'd be pretty easy. Kind of like our Van de Graaff generator. As we get close enough to it, there'll be an arc, or a jump of electrons from one side to the other. But what if I were to fill it up with something like plastic, or maybe glass, something that is a very insulated material, PVC. So the material of my dielectric would also matter, and that we're going to use a variable K. This K value you can find in Giancoli in our book, but then it's also multiplied by a variable on our formula sheet, which is E naught. You'll see it look like a funky E with a little symbol underneath it. E naught. So this is our value for capacitance. So do you remember how I told you guys that 1 farad was an unbelievable amount of capacitance that we could have? We're going to go through one example, and this is partially why. It was dependent, our capacitance was dependent based off of area, as well as the distance between them, and the material that we have. Our example isn't going to quite use this, but this is the size of a capacitor. Now, it's not very big, so the amount of area that it can hold isn't a whole lot, right? It's smaller than my pen cap. As well as the distance between them, well, that's also going to be pretty small. So here's an example that doesn't quite use the value for this capacitor, right? Here it is. Okay, so here's our scenario. We have two parallel plates, right? They are 20 centimeters tall by 3 centimeters wide, and they're separated by 1 millimeter. Now, the difference in voltage between one plate and the other is 12 volts. The first thing I want to find out is I want to find out how much capacitance there is. And I ended up writing out what our E naught constant is, which is 8.55 times 10 to the negative 12 coulombs squared per newtons times meters squared. So, let's go right into it. If we say capacitance is equal to, the K value for air, if you look it up, is 1.0006, which we can round that just straight to 1. Air and a vacuum are identical. We can round to make them both the same, a value of 1. So, if my K value is 1, I'm going to get rid of it. Now I have my short formula, and this is what I should get. So, now I've put all of my values into here. 8.55 times 10 to the negative 12, multiplied by 6.0 times 10 to the negative third, all over 1.0 times 10 to the negative third. Now this will give me a final capacitance of 5.3 times 10 to the negative 13th farads. That's small. Now we won't keep it in terms of times 10 to the negative 13th. What we're going to do is we're going to turn it into terms of picofarads, which is times 10 to the negative 12th. So in order for me to get times 10 to the negative 12th, I have to multiply by 10, and then I'm going to turn this into 53. So it's actually 53 picofarads. And this is a large area. This is 20 centimeters by 3 centimeters. And if we think of the capacitor that I just showed you, that's pretty darn small. But the difference is that that capacitor doesn't have air between it. It actually has something else to give it a better dielectric. Now the second part to this is I'm looking to try and find out how much charge is built up on each plate. And if we look back into what our charge formula that used charge and everything that we found, which we found our capacitance, 53 times 10 to the negative 12 farads, and I know my voltage, what we can do is we can put it right into a single formula, where we have our charge, which is what we're looking for, is equal to the capacitance multiplied by our voltage. Well, that should be pretty simple. All we're going to do is we're going to take 12 volts, multiply it by our capacitance, and I'm just going to skip a step and we're going to write out what the value is. And we get our charge to be 6.4 times 10 to the negative 10th coulombs of energy, of charge, sorry, not energy. Alright, now this last part, I want to find out how big my plates would have to be, how much area they would have to take up, in order for me to get 1 farad of capacitance. Keeping the same 1 millimeter in between there, still with air, still at 12 volts, I need to find out how much area it would take up. What we're going to do is we're going to look at our very first formula that we used. Capacitance, K, E naught, A over D. We're going to rearrange to get A, where now I have divided by E naught on both sides. My K value is 1, so that can be erased. I don't have a value. And my distance, I multiplied it by on both sides, so I get area is equal to CD over E naught. When we multiply all these values together, which my capacitance is not the same value that we had before, I really now want 1 farad. I want to find out how much 1 farad of capacitance is. My final answer will show up like this. So my area ends up becoming about 10 to the 8th meters squared. Well, let's think about, let's try and put this in terms that we can understand, because I don't know about what a square meter really is. So if we think about the area of a football field, the area of a football field is 5,350 meters squared. 5,350 meters squared. So how many football fields would I have to cover with my surface in order for me to get a 1 farad capacitance? Well, all I'd have to do is I'd have to divide these numbers, and I would get 10 to the 8th over 5350 meters squared, and that'll give me an answer of just under 187,000 football fields would give me a capacitance of 1 farad. So, a farad is a large value of capacitance. Now the last part I want to talk about is how much energy there is built up on a capacitor. And I think the best way to do it is to show it graphically. If we look at how much energy we have, how much work was required to move an electron through, or a charged particle through a difference of potential, we said voltage multiplied by the charge of my particle. Well, now my particle ends up becoming a plate. So instead of it being a lowercase q as a particle, it's now going to be a large particle. So I can find out how much potential energy my large particle has by knowing the change in my voltage that I had. So the second formula that I need to know is our formula for capacitance, where I said capacitance is the same as my total charge on my plate divided by the voltage that I have, the voltage difference between them. So, if I were to graph Q over V, I should get a linear fit. So let's do that. So I now have my charge on my vertical axis, I have voltage on my horizontal axis, and the slope of my line would be my capacitance. So, this is using the bottom formula. This is how I get my graph of, if I were to try and find my capacitance, I would do charge over voltage. And as I start off at 0, my voltage would be 0. The amount of charge that's on my plate is also 0. Then as I go up, I can graph my capacitance. But if I wanted to find out how much energy I have, how much potential energy is built up, I would have to find out voltage times charge. Well, if I'm using a capacitor, which now, if I wanted to find charge times voltage, I'm finding the area underneath my triangle. And you all should know what the area of a triangle is. So, my potential energy, this was potential energy in an electric field. My potential energy of a capacitor is equal to 1/2, right? 1/2 base times height. So I should have 1/2 voltage times charge. So, the amount of energy that I have stored up in a capacitor, 1/2 my voltage difference between my plates, multiplied by the amount of charge that I have built up on each plate. Now there's some equivalences that I can put into this formula. Suppose I didn't have one of these variables. Suppose I didn't have voltage, or suppose I didn't have charge. But I did have something like capacitance. Well, I could rearrange, and I could put capacitance in here. So let's say I rearranged and I got voltage by itself. And then I insert voltage is equal to Q over C into my formula where I see voltage. Well, then I could say, once I put in Q over C for my voltage, I would have charge times charge again, so I'd have Q squared over my capacitance. Now I think you can see what I'm going to do with this last one, where I'm going to rearrange and I'm going to get Q by itself. Now all of these are equivalent, but just to give you a heads up, we usually don't look at charge. Charge is something that is a little bit more challenging to measure than something like voltage or capacitance. We have a voltmeter. We can measure a voltmeter if we need to. We have a capacitor, so we can look at the capacitor and it'll tell us what the capacitance on it is, as well as we have tools to measure our capacitance. So most likely, the formula that you are going to see is going to be the voltage squared times charge. Maybe this one, but highly unlikely that you'll see the charge squared over capacitance. Even though it is correct, we won't see it very often.